Okay, so before we get into anything, I have a few announcements. So first is that the first homework is due tomorrow. If I added everyone to Gradescope who was enrolled on B courses like about a week ago, and if you weren't automatically enrolled to B courses, you'll have to add yourself manually, and the enrollment code is on the website. Okay, so feel free to email me if you have any trouble getting onto Gradescope, but the code is on the website. The first quiz is actually in a week from today. In class, it'll be the first 30 minutes, so we'll probably start right about now, go until 4:10. If you have any questions about that, feel free to reach out. But I'll make it pretty clear on Tuesday or at some point next week before the quiz on a Piazza post, sort of what exactly you will be expected to know. Okay, there aren't any like practice quizzes or things like that we could release because, we've never had quizzes in this class before, but it will be similar to the material you'll see in lecture and in homework. Okay, the first quiz isn't meant to be anything too punishing, I guess. Okay, and homework 2 will come out probably sometime on Saturday and will be due a week from tomorrow. Okay, and I recommend you start working on homework 2 relatively early because it'll serve as good practice for the quiz. Okay, and I can't guarantee that I'll do this every week just because it takes a lot of time, but I think especially for homework 1, it would probably be pretty beneficial if there was like a homework walkthrough video. So I'll try and get that done over the weekend and post that on the website as well, and I'll make you aware of that on Piazza once that exists. Okay, is everyone also on Piazza, because that's sort of where all the announcements will be. Okay, and if you aren't, the code is or the link is on the website. Okay, and so the textbook section, I'm editing it basically every day because I think of new ways to explain things or new things to add or remove. So make sure you're looking at that, especially for the stuff we're covering right now, these sets of numbers and propositional logic. There are just a lot of details that we can't dive too deep into in lecture, but I highly recommend you look at the textbook for that. Any questions regarding any of this? Okay. So I just wanted to take a look at the in-lecture quiz from Tuesday. So the question was, suppose A and B are finite sets, and suppose that A is a proper subset of B. What does proper subset mean again? Yeah. Exactly. So, and since these are finite sets, we can write this without any ambiguity. The number of elements in A is less than the number of elements in B. Is that clear? Okay. So select all that apply. There exists a bijection between A and B. That's not true, because for there to be a bijection between two sets, either infinite or finite, they have to have the same cardinality. Right? So that's not true. There exists an injection between A and B. That's true, right? And if you think back to the slides we had on Tuesday, we talked about for a function to be an injection, there has to be at least as many elements in B as there are in A, so that everything in A points to something different, right? So that's true. There exists an injection between B and A. Well, that's not true, because that's the opposite of the condition that we have. And there exists a surjection between A and B. We can't necessarily say that, right? For there to be a surjection between A and B, we would have this condition, right? There needs to be at least as many elements in A as there are in B, because everything in B needs to be pointed to by some arrow, right? And for that to be the case, however many elements we have in B, there needs to be at least that many in A. So there isn't necessarily a surjection between A and B. But is there a surjection between B and A? Yes, and it's because of the way the inequalities work out. Okay, so the correct 2 was that there is an injection between A and B and a surjection between B and A. Okay? Any questions with this? Yeah.
Is the injection between A and B the same thing as the surjection between B and A?
No, because it would be a different function. All we're saying right now is that there exists an injection between A and B, and there exists a surjection between B and A. And that's something we'll talk about in the next slide. Really. Yeah?
Can you generally say if there's an injection between A and B, that there will be a surjection between B and A?
Yeah, you can. Yeah. Okay, and so there are a couple things I wanted to clarify. So before we said that two sets have the same cardinality if and only if there exists a bijection between them. we're not saying that every function between the two sets is a bijection. Right? We're just saying if the two sets have the same cardinality, then we can create a bijection, or there exists a bijection. So for example, if A is 1, 2, and B is 3, 4, they have the same cardinality, so we can make a bijection, right? And so one such bijection could be f of 2 is 3, and f of 1 is 4. But it doesn't mean every function will be a bijection. So for example, we could have f of 1 is equal to f of 2 is equal to 4. That's neither an injection nor a surjection, but it's still a function between the two. All we're saying is that we're able to find a bijection between the two if they have the same cardinality, and vice versa. It's an if and only if. So if they have the same cardinality, we can find a bijection. If we can find a bijection, they have the same cardinality. And we'll talk more about what this if and only if term means, hopefully today, but if not, on Tuesday. Okay? And two, to prove that a function is a bijection, we have to prove that it's both an injection and a surjection. Okay? Because, the meanings of these two expressions are the exact same. A function is both an injection and a surjection, and a function is a bijection. Those two things mean the exact same thing. Okay? And there are separate things you have to do to show that a function is both an injection and a surjection. And to make that clear, I'll probably put a question on this week's homework where the function example won't be too crazy, but it'll explicitly make you show that the function is an injection and explicitly make you show that it's a surjection. Yeah. Yeah.
Does there have to be a single specific thing in the domain, or can there be multiple?
So just for the function, just to be a surjection, it could be multiple, right? Because, for example, if we want to zoom in over here, I'm so bad at drawing. Okay, whatever. Pretend that it touches the x-axis. If the codomain here is the set of non-negative real numbers, then this is a surjection, even though it's not an injection. Yeah. So we separately show that it's an injection and that it's a surjection, and together it means it's a bijection. Sounds good? Cool. So just to recap what we talked about at the end of last class. So we said the natural numbers, also known as the counting numbers, denoted by n, are essentially just the set 1, 2, 3, 4, blah, blah, blah. Okay, and this forms like the basis of countable or countably infinite sets, which we'll get to in just a second. Okay? Then we introduce this idea of whole numbers, denoted by n subscript 0, which is the union of the set of the counting numbers with the number 0. So it's really just 0 followed by the counting numbers, 1, 2, 3, so on and so forth. And so we raise the question, do these sets have the same cardinality? Right? It seems a little weird because the whole numbers have the element 0, whereas the natural numbers do not. But going back to this more abstract definition, that two sets have the same cardinality when there's a bijection between the two, we were able to find this bijection between the naturals and the whole numbers, right? And to make it a little more explicit, we have the naturals here, the whole numbers here. Our bijection really looks like this. Is that clear? And this is indeed a bijection. Therefore, the whole numbers are also countably infinite. Okay? So to elaborate a little bit more, we say a set is countably infinite if and only if there exists some bijection between the natural numbers and that set S. And if that bijection doesn't exist, we call the set uncountably infinite. Okay? And it turns out that the bijection doesn't necessarily need to be between the natural numbers in S. It can be between any other countably infinite set in S. So we could also do this bijection between the whole numbers in S or any other set that we show to be countably infinite in S. Okay? And additionally, because as we looked at last class, if a function is a bijection, that means it has an inverse. We can also find the bijection in the opposite direction, right? So instead of showing the bijection from the naturals to the whole numbers, we could have done whole numbers to the naturals, and the mapping would just be the inverse. In this case, if the forward direction function is x minus 1, the reverse direction would be x plus 1. Okay, and in most cases, the inverse will probably be a little more complicated than changing -1 to +1, but you get the idea. Okay? And another way to interpret a set being countably infinite is that we can find an ordering of the set, right? We can say the first element in the set is whatever the natural number 1 points to. The second element in the set is whatever the natural number 2 points to, and so on and so forth. And it might be a little hard to see in this case because we're really just shifting things by 1, but in the next set that we look at, the integers, it'll become a little more interesting. Okay? Lastly, there's a more general term that we can use to refer to sets that are either finite or countably infinite. We can call these sets countable. Okay, so countably infinite refers to, this idea of an infinitely large set that we can find a bijection between it and the natural numbers. A countable set is either countably infinite or finite. Okay, so finitely many elements. Okay, and if it's uncountably infinite, we'll just stick with the term uncountable. So any questions with all this? Yeah.
Are all finite sets gonna have a bijection with the natural numbers?
No, because the cardinality of a finite set will just be some number, and the cardinality of the natural numbers isn't any number, right? So it's something infinite, right? So that's a good point of clarification. Countable is really just the union of these two different sets: the set of all finite sets and the set of all countably infinite sets. Okay, so yeah, it's not possible for for example, the set 1, 2, 3. There's no bijection between this set and the natural numbers. It's still countable though because it's finite. This all good? Cool. And then lastly, we ended off with this example on bit strings. And a bit string is just a number written in binary. Bit string is just a term that we happen to use when we study, countably infinite sets. So, for example, 0, 1, 1, 0, 1. So the first question is, consider the set of all bit strings of length n. Okay? Is this set finite, countably infinite, or uncountably infinite? The set of all bit strings of length n. Actually, you know what? For both of these questions, discuss amongst yourselves for a minute or so, and then we'll come back together. One specific n. That's a good clarification. Okay, great. Let's come back together. Sorry, I would give you more time to talk, but there will be, many of these small opportunities for you to talk amongst the class, and I sort of want to get through as much as we can. Okay, so the set of all bit strings with length n for a specific value of n. What is that set? Finite, countably infinite, or uncountably infinite? Yeah, in the back.
Finite.
Finite. Why do you say that?
It should be the number of numbers that can be represented by that bit, so 2 to the power of n, I think.
Yeah, great. So this is indeed finite. And that's because if you give me a specific length n, so let's just say n is 8, the set of all bit strings of length 8 is just the set of all numbers. It's equivalent to the set of all numbers I could write in binary with 8 digits. And there's not infinitely many of those. It's just 0 all the way until 2 to the power of 8. Right? I guess 2 to the power of 8 minus 1. Is that clear? So, for example, given n is equal to 8, this set is equal to, 0, 0, 0, 0, 0, 0, 0, 0, dot, 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 all the way until, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And you're right that there happen to be 2 to the 8 numbers in the set, or 2 to the n in general, but you don't really need to know that for now. We'll talk more about things like this when we get to counting. Okay? All that we care about is that this is finite. Any questions with why For a specific n, the set is finite. Okay, what about part B? Consider the set of all bit strings of finite length, where the length could be anything. Is this set finite, countably infinite, or uncountably infinite? Countably infinite, okay? And the reason for that is the set of all bit strings are essentially just the binary representation of the set of natural numbers, right? So for example, let's just call it, again, this set S. We have, our mapping between N and S. Here we have 0. Sorry, that's not in the naturals. 1 gives you 1, I think. 2 gives you 1, 0. 3 gives you 1, 1, and so on and so forth. And that's a bijection. Is that clear? So if we don't specify the length n, and we're just saying all bit strings of finite length, there are indeed infinitely many of them, but it's a countable size, if that makes sense. Okay? I guess I should have mentioned this probably a week ago, but another term for a bijection is a one-to-one correspondence. Okay? So a one-to-one function is an injection. A one-to-one correspondence is a bijection. Okay? I don't really like using the term because if you say one-to-one, then sometimes it's ambiguous. Are you talking about an injection or a bijection? But I don't know. Out in the wild, you might see this. So any questions with any of this? So, countably infinite. Great. Okay, so the next set we want to look at is the integers. So the integer is denoted by this bold-faced Z, or Z, as we say back in Canada, is the union of the whole numbers with their negatives. Okay? So before, we just started with 1, 2, 3, 4, and then we, prepended 0 to that, and now we're extending infinitely in the other direction. So now you have -1, -2, so on and so forth. And so the question you want to ask yourselves is, are these integers, or the integers rather, countably infinite or uncountably infinite? Okay? And of course, if they're countably infinite, that means they have the same cardinality as the natural numbers, which, at least for now, not for now, but the only technique we've really used is showing that there's a bijection between the naturals and the integers. Okay? So I won't give you the answer just yet, but I want you to try and talk amongst yourselves and see if you can determine whether or not the integers are countably infinite. And of course, that means try and find the bijection. Let's go back together. So what do people think? Are the integers countably infinite? Raise your hands. Uncountably infinite. Raise your hands. Okay, so the majority of people seem to think that it's uncountably infinite. That's a blank slide. Okay, so it turns out the integers are countably infinite. And so we'll show how you get that bijection. Okay, so, let's get into it. So the way we'll show how this bijection comes about is by writing both the natural numbers and the integers in a very specific order. Okay, and actually, I'm not going to use the naturals, I'm going to use the whole numbers. But as we saw earlier, it doesn't matter. As long as I can find a bijection between any countable set, and I know the whole numbers are countable, this is fine. So let's start with the natural numbers and the integers. Okay, and let's go for it. Okay, so 1, 2, 4, 5, 6, 7, 8, and 0, 1, negative 1, 2, negative 2, 3, negative 3. Okay? It's annoying me. Okay? So I've written the whole numbers and the integers in a very specific way. Okay? And let's try and determine the rule that specifies this function. Let's write it like this. So we notice that the behavior is slightly different when our input is even and when our input is odd. Is that clear? Right? So first let's look at the case when our input is even. Okay? So in the case when our input is a multiple of 2, what are we doing to produce the output? And so this is what you've probably seen before as being a piecewise function. If n is even. Okay, so in the case that n is even, what are we doing to the input? Yeah. Yeah. So we're dividing by 2 and taking the negative of it. So we'll give you negative 1/2 n. So just to keep it consistent, we'll write it like this. Exactly. We're dividing by 2 and taking the negation. Okay? What about the other cases? So, in the case when our input is odd. Yeah.
You're adding 1 to n, then dividing by 2?
Exactly. Is that clear? So, for example, the way we get 1 from 1 is we add 1 to 1 as we get 2 and then divide by 2. The way we get 3 from 5 is we add 1 to 5 and then divide by 2. So in general, if n is odd, we say this rule is given by n plus 1 over 2. Okay, so now the question is this a bijection? Okay, it is, and we can sort of talk about it a little informally. So the first question is it an injection? And the answer is yes, because given my input, I'm never going to repeat the same output twice. So for example, the integer negative 3 will never be seen twice along this pattern. Is that clear? Right? And is it a surjection? Well, yes, because every integer will appear at some point out of this pattern. And how do I know that? Well, it's because the way I've written the pattern, you know that it will continue forever and ever. I'll eventually get to, negative 10,000, positive 10,000, so on and so forth. So whatever integer I want as my output, I know it'll appear somewhere in the pattern. And this function is just, algebraic representation of this pattern. Okay, so this is indeed a bijection. So therefore, the integers are countable. And we'll say countably infinite. Any questions with this? And so we also could have done, the bijection going the other way, right? Do you agree with that? So just to do it, why don't we try and find the bijection going from the integers to the whole numbers? Okay, so g of n, we'll say is what? Okay? So again, there are different cases for our input, right? So what's the first case? Yeah. Okay, so also just to introduce the notation, I'll say g of z. Okay, not that it really matters because a variable is just a variable, but f of n sort of implies that our input is a natural number or a whole number, and g of z might imply that our input is an integer. Okay, although z, if you take other classes, will often be used to denote complex numbers as well. Just showing you that it doesn't necessarily have to be n. Okay, so you're right. Our first condition is if z is less than or equal to 0. And in that case, what do we do? If z is less than or equal to 0. Yeah. Good. We multiply by negative 2. Does that make sense? Yeah. To go from negative 1 to 2, multiply by 2 and then negative 1. To go from negative 3 to 6, multiply by negative 2. So that looks right. So negative 2z. And I guess the other case would be if z is greater than 0. In the case where z is greater than 0, what do we do? Yeah.
We double z and subtract 1.
Exactly. We multiply z by 2 and subtract 1. Is that clear? And you might notice something a little fishy. Not fishy, but I can do this, I think. Cool. This, you see what I'm circling, right? Yeah, that and this are inverses of one another. And the second one, the case when n is odd, and this are also inverses of one another. Okay? So you can almost think of it as being two separate bijections, but it is a bijection even when you think of it as a whole function. Okay? So this just shows you can do it either way. If you can do it one way, by definition, you have to be able to do it the other way. This all good? Yeah. Why does there being a bijection mean that it's countably infinite? That's essentially our definition for what it means to be countably infinite. It's not that there's a bijection in general, but that there's a bijection between our set and the natural numbers, or some other countable set. So for example, I don't want to give too much away, but suppose you find some set that is not countably infinite. It might have bijections to another set, but just because that bijection exists doesn't mean those sets are countably infinite. A set is countably infinite if and only if you can make a bijection between the set and the natural numbers. Okay? Or between the set and some other countably infinite set. And what we did here was we know that the whole numbers, because we found this bijection here, the whole numbers are also countably infinite. And we showed the bijection between the integers and the whole numbers. Okay? So any other questions with that? Okay? So as we go through the next sets of numbers, the question you should be asking yourselves is this set countably infinite? And what that really means is, can I make a bijection between this set and the natural numbers? Okay. So the next set we want to look at is the rational numbers. Okay? So the set of rational numbers denoted by Q is the set of all possible combinations of one integer divided by another, with the latter being non-zero. And so this is the first time we're creating a set where we have to use set builder notation, right? Because there isn't really a way that we could list out the rational numbers. We sort of specify this rule that we use to generate rational numbers. It says, give me all the numbers of the form p divided by q, where p and q are integers and q is not zero. Okay? So now the question is, are the rational numbers countably infinite or uncountably infinite? Okay? That's the question we want to ask ourselves. So I'll let you discuss for a second, but before I do that, I want to show you this property of rational numbers that you may or may not have thought about before. Okay? Dense orderings. Okay? So we say a set S is densely ordered, okay, if it satisfies the following property. Okay? Upside down A, B, E, S, backwards E. What does this mean again? This says, for any two elements in the set, there exists some third element in the set that is between the two. Okay, so what this is telling me is that between any two rational numbers I think of, there's another rational number. Right? This is not true of the integers. right? Suppose I pick 2 and 3. There's no integer between them, right? But this property becomes true of the rational numbers because suppose m and n are rational numbers, then m plus n divided by 2 will also be irrational. Yeah?
Backwards E means this?
Yes. So this means for all. This means exists. And again, if you go to the textbook and go to section 1.5, it has like a cheat sheet of all of this notation, if you ever forget. Okay? And this colon, such that. Okay? To be a little more explicit, why do we say m is a1 divided by b1 and n is a2 divided by b2? Let's look at what happens when we divide m plus, or when we evaluate n plus n over 2. So m plus n over 2 is a1 over b1 plus a2 over b2 over 2. You got to do something like this. Okay? So this is the result I get. Keep it zoomed in. This is the result I get when I add m plus n and divide it by 2. And what am I getting when I add m plus n and divide by 2? It's the average of m and n, which you know, if m and n are different numbers, has to be between m and n. That's clear? Okay? And we know a1, b1, a2, and b2 are all integers. Right? And so this result, a1, b2 plus a2, b1 over 2 times b1, b2, the numerator is an integer because it's just the sum and product of integers, and the denominator is also an integer because it's the sum and product of integers. So this is indeed a rational number. Okay? So what this tells you is between any two rational numbers, you can find another rational number. And in fact, between any two rational numbers, there are actually infinitely many more rational numbers. Okay? So just to illustrate the point, why don't we look at 0 through 1. Okay? What's the average of 0 and 1? A half, right? And then what's the average of 0 and a half? A quarter. What's the average of 0 and a quarter? An eighth. And I can continue this for as long as I want. Right? I can keep following this pattern, which I'm really getting from 1 over 2 to the n. And even 1 over 2 to the 10 trillion, it's still a number between 0 and 1, and it's still a rational number. Right? Because it's an integer divided by an integer. So what this tells you is that between any two rational numbers, not only is there another rational number, but there's actually infinitely many more rational numbers. Okay? Is everyone clear on what this property means, densely ordered? Okay. So the question is, what implication does this have on the countability of Q? So discuss amongst yourselves whether or not you think that the rational numbers are countable or not. Yeah. Yeah, no worries. Yeah. Yeah. Oh, sorry. Okay, so it seems like talks have died down. So what do people think? Are the rational numbers countably infinite? Raise your hand if you think the rational numbers are countably infinite. Okay. Okay, now raise your hands if you think the rational numbers are uncountably infinite. Okay. I have bad news for you. Okay, so the rational numbers are also countably infinite. Okay? So really, the whole thing about dense orders was really just there to confuse you. Well, not confuse you, but to distract you, really. So this is a property that is true. This is a property that is true of rational numbers. That isn't true of the sets that we saw before, integers and whatnot. But it doesn't necessarily mean that the rational numbers are uncountable. Okay. So indeed, the rational numbers are countably infinite. Okay. And because I'm telling you they're countably infinite, that means we can find a bijection between them and the natural numbers. But we're actually going to approach this slightly differently. Okay. So our end goal, really, is to prove the following statement, right? That the natural numbers and the rational numbers have the same cardinality. Is that clear? Okay. And by the principle we saw, I believe it would have been on Tuesday, this is the combination of two separate inequalities, right? This is the combination of the natural numbers being less than or equal to the cardinality of the rationals, and vice versa. Is that clear? When we combine these two inequalities, we get this one up here. The fact that these two numbers are equal, right? And again, this is just a slightly more complicated way of saying if x is greater than or equal to y, and y is greater than or equal to x, this tells you that x and y have to be the same number. Any questions with that? So, yeah?
If you have an uncountable infinite set,
Yeah.
could you just expand the dimensions of the range? So like if you have like r squared,
Yeah.
you create a bijection between r squared and then an uncountable set,
Like, can you, if there's two uncountable sets, can you find a bijection between them?
what I'm saying is, if there's an uncountable set,
Yeah.
you create a bijection with a countable set of like r to the n.
But R itself is well, I didn't tell you that yet, but R itself is uncountable.
Oh, okay.
Yeah, we'll talk a little bit more about that in just a second. Yeah.
Where do you get those inequalities from in the first place?
So, okay, good question. So we got these from talking about injections and surjections. Okay, so I guess we can even go back to that slide. Let's find it. So we talked about before that if there's an injection between A and B, the cardinality of A has to be less than or equal to the cardinality of B. Okay? And we also said if there's a surjection between A and B, the cardinality of A has to be greater than or equal to the cardinality of B. Okay? And we put these two things together and said that if a function is a bijection, the cardinalities have to be equal. And so that's sort of where this is coming from. And so what I wanted to get at now is for the cardinality of the naturals to be less than or equal to the cardinality of the rational numbers, we don't actually really need to do a proof of this, right? Why? It's because we know the natural numbers are a subset of the rational numbers, right? Is that clear? Every natural number can also be written as a rational number, right? If you wanted to find an injection, right? If you want to find an injection from the naturals to Q, what you can do is just take a natural number and send it to n over 1, which is just an explicit way of saying that every natural number is also a rational number. You can write it as itself divided by 1. Right? So if we want to be a little more formal, since we can find an injection from the naturals to the rationals, that means the cardinality of the naturals is less than or equal to the cardinality of the rationals. Right? Is everyone okay with that? It's the exact same principle as the slide from last week or last class that I just showed. If there's an injection from A to B, the cardinality of A is less than or equal to the cardinality of B. And so now, what we really need to focus on is the second one. We need to somehow show that the cardinality of the rationals is less than or equal to the cardinality of the naturals. And how can we do that? We can do it by showing an injection in the opposite direction. Is that clear? So what we're really hinting at here is if I can find an injection from A to B and an injection from B to A, then there's a bijection between A and B. Is that okay? And we're really just getting that from these two inequalities. Okay? And I just showed you the injection from the naturals to the rationals. I just take a natural number and send it to itself. This is definitely not a bijection. It's not a surjection, right? Like, for example, 2/3 will never be the output of this. But it will never send two unequal natural numbers to the same output. So it's an injection. Okay, there's a special name for this. It's called I forgot the name of it. But there is a name for it. Okay? Not that important for now. Okay? Really, our question now boils down to finding an injection between the rationals and the naturals. Okay? So try and think about how you can find an injection from the rational numbers to the natural numbers. Okay? And again, our end goal will be able to write some sort of chart where we have the rational numbers here, some order of the natural numbers here, such that the function given by this chart is an injection. And we're going to do it on the next slide, but I want you to think about it for a second. So talk amongst yourselves. Okay. So, again, right now we're trying to find an injection from the rationals to the naturals. Okay? How many of you, when doing so, you thought of this picture? Anybody? No? Okay. Let's interpret this. Okay. So, at a high level, what we're doing is creating this path that will traverse the Cartesian plane. Okay? And do you agree that, if I continue this path infinitely long, I will eventually reach any ordered pair you give me? You agree with that? Because it's, comprehensively going through every single possible point, right? In some sort of ordered fashion, right? First it's going, at the points, within this square, and then within this square, and so on and so forth, right? So eventually, it'll get to whatever point you give me. So how we can create this injection is we'll say a point represents a rational number. Okay, so give me the point a comma b. I'll say that this represents the rational number a divided by b, or b divided by a. It doesn't really matter. Okay, I'll say b divided by a because, you find the slope of the line between it and the origin, I guess. Doesn't really matter. What I'm saying is each of these points really represents a rational number. And so what this spiral really tells me is that this is a way of of enumerating all of these rational numbers. Okay, so let's do it. So let me set up a chart here. Q, maybe give me a little more space. N. Okay, and so as I see a point, I'll add it to this left column. One thing I have to be careful of is not repeating points. So for example, the point 2 comma 4 and the point 3 comma 6 both represent the same rational number. Is that clear? But that's okay. We can be cognizant of that and only write down a rational number the first time we see it, which equivalently is writing it down in its lowest form representation. Okay, so let's do it just so that we have something concrete down. Okay, this is my first point, 0, 0. We can just call that the first number we see. Okay, so that will be the rational number 0. Okay, this point here, 1 comma 0, what rational number does that represent? 0, which I've already seen, so I'm just going to ignore it. Okay, so I'll circle all the ones that we count. This number here, 1 comma 1, what does that represent? 1. Okay, so I'll say put 1 here and 2 here. Really, this doesn't require much thought. Okay, this point over here, what does that represent? The point 0 comma 1. Nothing, right? Because that's 1 divided by 0. It's not in the set of rational numbers, so we'll ignore that. And really, we'll ignore everything from now on both the x-axis and the y-axis. Right? Is that clear? Everything on the x-axis is 0. Everything on the y-axis is undefined. Yeah?
I guess I was going to say that would it not be by injection if you see the number? Like if we're to prove since it's an injection in the other direction.
We showed the injection in the other direction, so all we need to show is that this is an injection as well. Great point. Okay? Let's do this until we get to some fractions, just so you're convinced that every fraction will appear. Okay? That number is not going to appear. Okay, what if I look at this point? Negative 1 comma 1. What point is that? Or what number is that? Negative 1, right? Cool. Then we look at this point. Not going to really appear anywhere. This point that I'm hovering over right now, what is that the representation of? 1, right? Which is negative 1 comma negative 1. Going to skip that. Then I come over here. What is that? It's on the y-axis, so I skip it. Then I come over here. I have the point 1, negative 1, which is negative 1, which I've already seen. Then I come over here, and I see my first new point in a while. Okay? What point is this? Well, the coordinates of it are 2 comma negative 1. Right? So by this mapping, that's negative a half. Is that clear? So I'll come over here. The point's coordinates are 2 comma negative 1. So I'll come over here and write negative a half. Okay? Go back on the x-axis, don't really care. Come up to this point. Now I have 2 comma 1. What point is that? 1 half, right? Because the representation of this point, 2 comma 1. Okay, so we'll go a half. And, just so we have one more on the board. Okay, this one again we skip because really anything on this line here will represent the point 1, or the number 1. Because the x-coordinate and y-coordinate is the same. If you divide them, you'll just get 1. Okay, so now let's check this point. What are its coordinates? 1 comma 2 looks like the number 2 to me, right? X is 1, y is 2. Divide y by x, we get 2. So here we have the point 1 comma 2, and we get 2. And you see, if I continue this forever and ever, every rational number will appear somewhere on the left-hand side, right? So this is indeed an injection from Q to N, because it's never the case that 2 different rational numbers are at the same point on the spiral, right? The outputs, the natural numbers, are the positions in the spiral. And if it were ever the case that 2 inputs had the same output, it would just mean that 2 numbers were at the same point in the spiral. But there's only 1 point at each point in the spiral, right? So this is definitely an injection. Yeah?
Is there a function that can give us the inputs of Q without outputs?
Okay, so this is actually a function, right? Because remember, at a very abstract level, all a function is a subset of the Cartesian product of Q and N. If your question is there an algebraic representation of this? Maybe is probably the only answer I have. Right? Like there are definitely some patterns in here, and you could formalize this if you want, but that's not required to make it a function. Like this, like what we have here, is as much of a function as f of x is equal to x squared, right? A function is just the subset of the Cartesian product. Yeah.
Doesn't have to pass the vertical line test to be a function?
So the spiral is not the function itself. What the function is are the points that I have written over here. Yeah. Good point. What am I saying? Good point.
I might have missed something.
Yeah.
I still don't understand why naturals are subset.
Sure. So we want to go back here. So the question is, why is it true that the naturals are a subset of the rationals? Okay? Well, so the natural numbers are just the numbers that we write 1, 2, 3, 4. That's okay, right? And the rationals are all the numbers that we write as P over Q, where P and Q are both integers, and Q is non-zero, right? Is that okay? Well, if you want to show that the naturals are a subset of the rational numbers, all you need to show is that, for example, give me any natural number, tell me that it will appear as a rational number. But if you give me any natural number, I can write it as it divided by 1, which is just integer divided by integer, right? N divided by 1. If your favorite number is 23, well, that's just 23 divided by 1, which is also a member of the rationals. Is that clear?
So it
Okay.
also goes up, right?
No. So, for example, 2/3 is a rational number, but it's not a natural number, right? Yeah.
In the this diagram,
Yeah.
all those points that are between like 0 and 1 and 0, they're also going to be included, right? Like, because that's the only way we're going to get all kinds of rational numbers.
So you mean points like 1 over 2 to the 10 or something?
Like 0.5, like 0.5 comma 0 or like 0.25 comma 0.
No, because so 0. No. Okay. So this process will certainly reach every single rational number, and we can do so only by looking at the lattice points, which are points with integer coordinates. Because if it's a rational number, it can be written as some integer divided by some other integer. Is that clear? And you said something about 0.5. Well, that's just 1 divided by 2. And when we get to the point where if it's 1 divided by 2, when the x's are 1's, y's are 2's, or vice versa, we'll get to that point, right? Because the definition of a rational number is some integer divided by some other integer, we will always we will at some point along this process hit every single rational number. Yeah.
Can you draw like a sketch of it?
Of this function?
Yeah.
Like, am I able to? Yeah. I don't know if you really want to, we can. Like, okay, 0, 1, 1, 2, -1, 3. Like, you can go through and do it, and it is a function, okay? Because, for example, I guess the two things we have to show is, since we're only looking at the lowest form representation of each rational number, there will never be repeated elements in our domain, right? Because, for it to be a function, no two, like an input can only have exactly one output, right? And because we're skipping every time we've seen a rational number that we already have in our list, that's not going to be an issue, right? Like, since we already saw the point 1, 1, we're going to skip -1, -1 because it would represent the same rational number and it would make it not a function. So we skip that. We just care about the lowest form, first representation of each number that we see. Okay? I'm not lying to you. This is a function. If you really want, you can draw it out. But I think one of the main things you want to get from this class is that it doesn't need to be written as f of x is equal to something for it to be a function. Okay? This is perfectly valid function. Is that clear? Yeah.
The slide before you wrote that the natural numbers are a subset of the rational numbers.
Yeah.
I get why that is, because there's more rational numbers, like, as the natural numbers is. But how can their cardinality be equal if it's not a proper subset?
It is a proper subset.
Or yeah, if it is a proper subset.
That's the weird thing with infinity, right? Even like you could make the same argument with the whole numbers. The whole numbers, the integers are what am I saying? The natural numbers are a proper subset of the whole numbers, but they still have the same cardinality, right? Naturals are proper subset of the whole numbers. And for that matter, they're a proper subset of the integers and rational numbers, right? But since we found a bijection between them, same cardinality. What we did here is we didn't do it by explicitly finding a bijection, but we found an injection going one direction and an injection going in the other direction. Yeah?
So that should say proper subset, or?
Yeah, sure. This doesn't mean that like this is just saying that it's a subset. Okay? And since there's an equal sign here, there's not an equal sign, but like an equality indicator, we have it in both, right? If you wanted to be more specific, yeah, you could say that it's a proper subset, but just saying it's a subset is fine, because it is a subset. Okay? And so to recap, since we know that the naturals are a subset of the rational numbers, the cardinality of the naturals has to be less than the cardinality of the rationals. And if you wanted to be more convinced, we can find this injection that sends a natural number to it divided by 1. Cool. And then this weird spiral thing is our injection going the opposite direction, going from the rationals to the naturals, which tells us from the rules we saw before, the cardinality of the rationals is less than or equal to the cardinality of the naturals. So that's what we have here. And putting these two pieces together from this property over here, we have that the rational numbers and natural numbers have the same cardinality, telling us that the rationals are countably infinite. Okay, so to recap, essentially what we did was we showed an injection in one direction and an injection in the other, which effectively tells you that there exists a bijection between the two. We didn't have to find it, but we know since there's an injection one way and an injection the other way, there is a bijection between them. And so that they do have the same cardinality. Okay? Yeah?
Does that mean there's like also a surjection?
Yeah, there is. We don't have to find it. It just happens to be true. Yeah?
Can you give an example of a set that is uncountably infinite?
We're going to do that very shortly. Okay, so any questions with this? And I agree, it's a lot to take in sort of at once, but I highly recommend looking at this section in the textbook. It gives a few more analogies and it might make things a little more clear. So I highly recommend you look at that. Okay, so the last set, or the last couple sets we're going to look at right now are the real numbers. So the set of real numbers denoted by R is a set of all possible distances from 0 on a number line. That's one way to put it, right? Yeah. So that's a pretty abstract way of defining the set, but it'll suffice. And I think you know what I mean when I say the set of real numbers, right? All possible distances from 0 on a number line, right? And so there's no set builder notation I could use to construct the real numbers. So I just give some examples and put comma, dot, dot, dot. Okay, we have some examples. 3, pi, negative root 63, so on and so forth. Okay, and just so that we round everything off, we have the irrational numbers. So we have the set of irrational numbers, which is denoted by the set difference of R and Q. Okay, so we probably won't talk about them enough for them to have their own symbol, but you can think of them as the set of real numbers after you get rid of everything that's a rational number. So it's a real number that's not rational. Hence the name irrational. Okay? So those are our definitions. And so the question is, are the real numbers countable? And the answer is no. Okay? But I know this is kind of anticlimactic, but the proof is probably a little more involved than we need to get to in this class. But if you're interested in searching it up, reading it on your own, it's linked. If you go to 1.3 in the textbook, I have a link to the section of the CS70 notes where they talk about this. It's called Cantor's diagonalization. Okay? And so the general gist of it is we'll do what's called a proof by contradiction. Okay? So don't worry too much about what that is now. We'll talk about that in maybe a week or so. But essentially, we will assume that the real numbers are countable. Okay? So let's just say, for the sake of a counter argument, say the real numbers are countable, and we'll do a bunch of valid steps, and then arrive at some contradiction. Okay? So the general gist of it is, okay, let's assume the real numbers are countable. You do something else, and that tells you the Earth is flat. That's not true. So the initial thing you started off believing is not true. Okay? That's sort of how a proof by contradiction will work. Okay? We won't talk too much about it now, but feel free to read it if you're interested. Okay? And if this wasn't, actually, there's a diagram that'll come that will make that a little more clear. But okay. So again, real numbers are not countable. Happens to also be the case that the irrationals are not countable. Rationals, of course, are, which we did all that work for. Irrational numbers are not countable. Okay? And so there's this last set, which is sort of just in here for fun. It's a set of transcendental numbers. Out of curiosity, how many people have heard of transcendental numbers? A few, okay? So a number is transcendental if it is not the solution to a non-zero polynomial equation with integer coefficients. Okay? So we can say if you can come up with some polynomial where all the coefficients are integers and t is a solution to that polynomial, then it's not transcendental. But if it's not a solution to that, it is transcendental. So for example, we know square root of 2 is irrational. Okay, and a proof of that is like basically the first proof that we'll do at some point next week. But it's not transcendental, right? Because if I look at the equation x squared minus 2 is equal to 0, the square root of 2 is a solution to that. Okay? So even though the square root of 2 is irrational, it's not transcendental. Because this is a polynomial with integer coefficients, 1 and 2 are integers, and square root of 2 is a solution to this, therefore it's not transcendental. So pi and e are some of the only examples of transcendental numbers that mathematicians know of. Because it's extremely difficult to show that a number is transcendental. Okay? But essentially what this is saying is that it's impossible to come up with a polynomial where all the coefficients are integers and x is equal to pi will satisfy the equation. That's what they're saying. Okay? For example, like x squared minus pi squared is equal to 0. Sure, pi is a solution to that, but I said all the coefficients have to be integers. Pi squared is not an integer. Is that clear? Okay. So the set of numbers that are not transcendental, okay, which is all rationals plus things like square root of 2, we call them algebraic numbers. Okay? I don't know how much we'll talk about this in the class after, 30 seconds from now, but I think it's interesting for you to know. Okay? Now that you all laughed, there will be a homework question. So any questions with what a transcendental or algebraic number is? Okay? Just to make it clear, the union of all algebraic numbers and transcendental, the real numbers. Okay, I had to say real transcendental numbers because a number could be complex and transcendental. Okay, don't worry too much about this. Okay, and yeah, I also should have mentioned, if a number is rational, it cannot be transcendental because if it's written as a over b, well then bx minus a equals 0, it'll be a solution to that. Right? So, and that's a polynomial with integer coefficients. Okay? So this picture sort of summarizes all of the sets that we've seen so far, minus the transcendental numbers. And, to put it symbolically, we can say the naturals are a subset of the whole numbers. Proper subset, I guess. Proper subset of the whole numbers. Proper subset of the integers. The rationals of the reals. Okay? And the ones that are countable are these. Oh, that's a terrible choice of color. Countable. Okay? And if you're interested in seeing where complex numbers fit into this, there's an appendix section in the textbook. There's 2 of them. One about complex numbers, one about series and sequences, about sigma and pi notation, which will be useful maybe in 2.5 weeks from now. So I'll refer you to those when I think it's necessary. But feel free to look at the one on complex numbers. But there isn't really a whole lot to it. The complex numbers are a superset of the real numbers. And the real numbers themselves are uncountable. So the complex numbers will also be uncountable. Question?
Was irrational numbers countable?
Irrational numbers? Uncountable. But don't worry too much about the irrational numbers. So any questions with this hierarchy of numbers that we've looked at so far? Okay, cool. So the key takeaways are, one, that not all infinite sets have the same cardinalities. There are different levels, if you want to think of it like that, of infiniteness. For our purposes, we'll classify everything as being either countably infinite or uncountably infinite. Okay? And these first four sets that we looked at, up until the rationals, are countably infinite. The reals are not countably infinite, so they're uncountably infinite. And just as a reminder, for example, this on its own, in the cardinality of the natural numbers, has no meaning for us. We can only use it in comparison to the cardinality of another set. So for example, the cardinality of the rationals or the cardinality of the integers. Okay? On its own, this doesn't really have a value. Is that clear? Any questions with all that? Okay, so I'll give you a couple minutes to do attendance, and then I want to start propositional logic a little bit. A lot of the homework, I'll tell you now, revolves around propositional logic. So for some questions, you might have to wait until Tuesday to be able to do them. But with 10 minutes, we probably will have enough time to do enough interesting things. Yeah. Sure. Let me write the link on the board. Who here follows the NBA?
What does free false mean?
False is a player who got traded. You'll see basically every URL that I make has some NBA reference. Actually, if we get to it today, there will be a pretty big NBA reference in here. The last link, we want AD. So the Lakers are trying to trade for Anthony Davis. The deadline was today at noon. So it didn't happen. So I'm sad. Also, the All-Star draft is like right now. I kind of wanted to watch it, but I was like, I have to come here and talk to all of you, so can't really do that. Okay, let's get into propositional logic. I want to see how much we can do in the 11 minutes that we have. Okay, and make sure to fill that out. Okay, so the last sort of bit of this course that we'll need before we start talking about proofs formally is propositional logic. It's very intertwined with set theory. Basically everything that we'll do going forward will have some sort of parallel to set theory, including De Morgan's laws. If you remember, I introduced probably a week ago from today. We'll see that sort of thing again. And again, highly recommend the textbook for this. It has a lot more examples than I can sort of cover in person here. And 1.5 has a summary of all the notation that we've seen. Yeah.
The book is still incomplete, so how far have you completed it?
Basically all of chapter 1 and chapter 2. So the stuff that we'll do, counting and that sort of thing, I still need to update it, but it'll be done by the time we get to there in the course. Yeah. So for all the stuff we've covered so far, it's all good. Okay. I don't know why there's a blank slide. Okay. A proposition. Okay. So a proposition is a statement that has a definite value. Okay. It's either true or it's false. Now this is in contrast to an opinion, which may have a different truth value. So what we call this is the truth value. An opinion will have different truth values based off of, who you ask. Okay? So the question is, are the following statements propositions? 13 is prime. It is indeed a proposition. 12 is prime is also a proposition. It's not true, but it's still a proposition. Is that clear? So it doesn't have to be true or false for you to determine if it's a proposition. It's just, is it a proposition? Does it have the value of either true or false? So yes. Okay? X is prime. So this is a special type of proposition that depends on a variable. Okay? This is a proposition that will usually denote as P of X. Okay? So given some assumed to be numerical value of X, can we tell definitively whether or not it's prime? Yes, right? So that's a proposition, right? On its own, X is prime without any other context. You might think that it's not, but virtually always, these variables, will be accompanied with some sort of context. So we'll usually use P of X, this like function notation, to denote this proposition that depends on your input variable X. Okay? It is 93 degrees outside right now in Berkeley, California. That sounds like a proposition. Either it's true or it's false. And here's the one that I was mentioning before. LeBron James is the greatest basketball player of all time. Okay, so that's not a proposition. Although, I think it's true. Not a prop. Okay? So the last one is more of what we would call an opinion. Okay? It doesn't have a definite truth value. Yeah. Maybe one day it will. But okay. Any questions with what a proposition is? Okay? So how we will use these propositions is we will combine them with these three operations that sort of that form the basis of everything we'll see in propositional logic. Okay? And I sort of already touched on some of these before, but there are three. There's the conjunction, the disjunction, and the negation. Okay? And they all have parallels in set theory. Okay? So the first one, A upside down V B, which we actually read A and B, right, is a conjunction. So the truth value of the statement A and B is true only when both A is true and B is true. Is that clear? What you can do is think of all of these as functions of your variable A and your variable B. So if I guess I can introduce this here. This structure is what we call a truth table. Okay? And A either is true or false, right? Because it's a proposition. And B is also true or false. It's also a proposition, right? A, B propositions. Okay? So if A is true or false and B is true or false, how many combinations of inputs do I have? 4, right? And it's these precisely. True, 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 false, false, true, and false, false. Okay? Those are you can think of A and B as being a function of your two variables, A, which is either true or false, and B, which is either true or false. Okay? And the way we define the conjunction A and B is that it's only true when A is true and B is true. Is that clear? So the output value is true when A is true and B is true. Otherwise, it's false. So these will all be false. Is that clear? And that's a definition of this conjunction operation. Yeah, you had a question?
Can you represent can you swap the upper arrow and the lower arrow with plus and a dot?
So are you in E16B?
Yeah.
Okay, so that's what I thought. That's very related, and those you're talking about those like NAND gates or something like that, and ones and zeros. They're effectively the same thing, but in a more mathematical context and like a less like circuits context, we usually use these symbols. Okay, just so that we don't get confused with A plus B or things like that. Let's try and use this notation for our purposes. Also, just to acclimate you to this sort of thing, which we'll see in future courses. Okay, so this is a definition of the conjunction operation, and where have we seen this before? Well, this was related to the set intersection, right? We said the intersection of A and B is the set of everything that's in A and in B. Is that cool? So it's very related to the intersection. Any questions with that? Okay. There's also the disjunction, which we read as A or B, And what operation is that related to? The union, right? So we have A, B, so X is in A, or X is in B. Okay? And so I actually want to write out the truth table for A or B as well. Let's change this. Actually, we can add a new column. Why don't we do this? Okay, let's add a new column for A or B. So this is true when at least one of A or B is true. Okay? So the truth value of A or B is true when they're both true, but it's also true when only one is true or only the other is true. So essentially, it's only false when they're both false. And that's just how it's defined. Is that clear? So here, both must be true, at least one. Okay? And my usual analogy is, which I think I mentioned before, you go to Subway, you get the combo, they ask you for chips or a cookie. That's a different type of or. There it's exclusive. You only get either the cookies or the chips. Right? Here, I guess this is not Subway because it's true when both of them are true as well. So it's not exclusive. Okay? Any questions with the definitions of A and B and A or B? Okay? And lastly, we have the negation, which just flips the value of A. So if A is true, the negation of A is false. If A is false, the negation of A is true. And on its own, it's not that useful, but what you'll see is we'll do things like the negation of A and B or C. Like we'll do complicated things like that and try and interpret that, right? And so just to give you the set theory parallel, this is related to the complement, right? So the complement of A is a set of everything that's, is in not X is in A, but also in the universe. Okay? So the complement of our set A is a set of everything that's not in A, but also in the universe. Okay, and we really don't need to include that because it's sort of implicit. Okay, so why don't we try and interpret this statement? Okay, so why don't I add meaning to each of these? So what if we say U of X is less than or equal to 100, E of X is even. Can you see what I'm writing? Yeah, okay. And P of X is prime. Okay? So each of these are propositions that depend on our variable X, right? Given a specific value of X, I can definitively tell you the truth value of any of these three things. And so this entire expression is also a proposition. Okay? And given a value of X, it also has a concrete value. It's either true or it's false. Of course, it'll depend on your value of X, but it's still a proposition. Okay? So can someone try and interpret what this means in English? Yeah.
X is less than or equal to 100 and X is even, or if it's not the case, that X is prime.
Exactly. So what this is saying in English is that X is under 100 and it's even or not prime. Is that clear? I sort of read that in order. Okay? We'll probably end there. Again, the quiz is in 1 week from today. Let me know if you have any conflicts or anything like that. Homework is due tomorrow night at midnight on Gradescope. Homework 2 will come out at some point over the weekend. And please enroll in the units for the course if you have not yet already done that. And email me if you don't plan on doing so. Okay, enjoy your weekend.